Hello everyone. So in this video I'm going to be looking at the suggested problems from chapter 35. So these are two problems from the book, problems 10 and 44, plus an additional problem that I borrowed from another book. It was in fact from Eric Mazur's Physics Principles in Practice. Okay, so the first problem, problem 10, is we have a single slit that's 1 millimeters wide and is illuminated by 450 nanometers light. What's the width of the center maximum in centimeters in the diffraction pattern on a screen that's 5 meters away? Right, so this is a straightforward application of one of the basic formulas in diffraction. So this is problem 10. And we have this single slit. And we have a screen, and it's going to produce a pattern of center maximum and then secondary minima and so on and so forth. And yeah, it's gonna be sine theta is m lambda. So this is the basic formula that we're going to use. So what are they giving us? They're giving us the slit width d is 1 millimeter. So this is 10 to minus 3 meters. And let me get this problem. And they're giving us the wavelength 450 nanometers. Yes, 450 nanometers. And they're asking for the width of the center maximum in centimeters. So they're asking for this. Now, if you remember, this was a long time ago, I admit, but this is very similar to one of the examples in the book. It's, I think, actually the first example. So it's example 35.1. Right? So as a refresher, if you had difficulty with this before continuing with this video, you might want to actually check that example out and try it again. Okay, so the D is this. Just D. And they're asking for the width. Let's follow that example's nature, and they're asking for what 2x is. Alright, so the one way to look at this is just going about this honestly, but I'm going to actually use an approximation which you're not allowed to use in this example because they're using a very, very narrow slit, but here our slit width is 1 millimeter, so I think the approximation is going to be appropriate. So what we need to find is to find the location of the first minimum on two sides, which is of course symmetric, and then we're going to find this distance, and we're just going to multiply it by 2. Right, so the angular direction of that first minimum is given by this formula, and so the order of the first minimum there is m is equal to 1, and what we are going to do is that sine theta is equal to m is 1 is lambda by d. Right, so lambda is 450 times 10 to minus 9, d is just 10 to minus 3. This is 450 times 10 to minus 6. Right, the meters cancel. This is a very small number. And for small numbers, theta is equal to sine theta, which is equal to tangent theta. All of these numbers, when you're writing theta in radians, are very similar to each other. So I'm going to say this is approximately equal to tangent theta. And tangent theta is, of course, equal to x divided by the distance. So let's call this L. I think they're also giving the distance to, yeah, and also L is equal to 5 meters. So tangent theta is just x over L. So therefore, 2x is just L times tangent theta, and this is going to be 2 L times tangent theta, 2 times 5 times 450 times 10 to minus 6, so this is 10, this is going to be 450 times 10 to minus 5 meters, but they're asking this in centimeters, so this in meters is going to be, so 10 to minus 5, and I turn this to centimeters, it becomes 10 to minus 3, and this becomes 0.45 centimeters. That's the width of the central maximum. Now, in the example 35.1, you are not allowed to make this approximation because they are using a much narrower slit width, I think slit width is like 10 to minus 3 millimeters rather than 1 millimeter. And so this is really wide, and you can't make this approximation. So here you can also try to come up with you can try to come up with a solution that doesn't use the approximation. And the way to do that is to express your tangent theta in terms of sine theta. How do you do this? Well, this is a trick that you might remember from high school. So you draw a right triangle, and you write everything in terms of sine theta. Right? So what you're going to do is that this is your theta, this is your sine, and let's say, how do you go about this? This is your sine theta, if this is just 1, and this has to be 1 minus s squared. Right? So in such a triangle, this is s, 1 minus s squared square root, this is going to be 1. The sine theta is just going to be s. Right? But tangent theta is then going to be s divided by 1 minus s squared square root. So this is sine theta by 1 minus sine squared theta squared. Right? You can of course recognize that this is just cosine theta, and tangent theta's definition is sine by cosine theta. But this is the general method on how you would arrive this. So after calculating sine theta this way, you can actually calculate tangent theta explicitly, and then substitute that in here to get your answer for 2x. And I assure you it's going to be something extremely close to 0.45. It's actually equal to 0.45 using the uncertainties given in the problem. Okay, so the next problem is so missing orders. Right, so missing orders occur for diffraction rating when diffraction minimum coincides with the interference maximum. Let capital D be the width of each slit and D is separation of slits, and you're supposed to show that there's some relationship that holds, and discuss the case of a special thing. Yeah, you're supposed to show some formula, and yeah, see what's going on. Now, this I'm not going to solve this problem completely, but I want to discuss what's going on here. So let me just freeze. I'm just going to give you enough information that you can actually follow the discussion in the solution manual. This is, I think, an interesting problem. It's also a practical problem when you're designing a diffraction rating experiment. This is something you would encounter. So this is problem 44. So what are we talking about here? So let's say that I have a diffraction grating, right? Something like this. So I have these slits that are separated by a certain distance and have a certain width. So their slit separation, which I measure from the center of the slits, is given by small d. And the slits themselves are just capital D. Right? Let's make sure that I actually get this right. Let the width of each slit and the separation of slits. Okay. So when we write down the formula for the diffraction grating, what do you get? Well, so if you actually look at the book for diffraction grating, you will get some formula. The principal maximum are at sine theta m lambda over d. Sine theta equals m lambda over d. Right. So this is what you get. Now, what is the assumption that goes into this? The assumption that goes into this. So you're looking at. So you have some screen here. You're looking at the light that's going in a particular direction from each slit, and you're saying that if the path length difference between all these light rays or all these lights is just a fraction, is an integral multiple of the wavelength, then you're going to get constant interference. You're going to get some maxima, and in between you're going to have disruptive interference, and you're going to get very clear, very well defined maxima as you increase the number of slits. Right. But now the assumption that you're making here, the implicit assumption that you're making here, is that out of each slit, by Newton's principle, you're going to get some plane wave, right? And if you are actually getting a plane wave from each of these slits, indeed, then these can actually interfere constructively when the path difference between all of those is an integral multiple of the wavelength. However, in reality, because of the finite width of these slits, you are not going to be getting perfect circular or spherical waves that's coming from these, which will then turn into plane waves in the large distance. Right? So what is going to happen is that you're going to get a diffraction pattern out of this. And the diffraction pattern, so remember what the diffraction pattern looks like. So there's a central maximum and then the secondary minima is far from uniform. Right? In particular, in some directions, you're going to get zero light. Right? In the minima of the diffraction pattern that's produced at each of these slits, even though those directions might correspond to the path difference between the slits of integral wavelength, you will not get any light. Right? So if you're getting some light in that direction, like the central maximum cannot be, but the secondary maxima or the third order, fourth order maxima, if they actually happen to be in the direction where you have a path difference of integral wavelength, then you are going to get constructive interference because you have some light. But if that direction happens to correspond to the minima, the dark fringes of the diffraction pattern that you get in each slit, then you're not going to get anything. You're not going to get your interference maximum because there is no light to interfere constructively. There is no light coming in that direction from any of the slits. For all of these slits, they have the same width, they have the same capital E, and so they're going to have the same diffraction pattern, and in the same direction that when one is producing its first minimum or the second minimum or the third minimum in either direction of their central pattern, all of them are going to produce their minima, and it will have no light to interfere with. So that's what they're saying. So this is what they're calling the interference maximum. Right? This is the interference between different slits, and within each slit, we're going to have a diffraction pattern. So the necessary condition for this to be an actual maximum is that for some light to be present. Right? So this is kind of self-evident, but that's what they're asking about. So I'm elaborating on a point perhaps too obvious. So if that condition is not satisfied, then you can't get constructive interference. If you have no light, you can't get constructive interference. When you have no light, well, then you have these minima in the diffraction pattern, right? And they correspond to a certain direction. If that direction coincides with this because of some special relationship between this capital D and small d, then you're going to get this funny pattern. You're going to actually get that relationship that's shown in the book. Okay, so hopefully this is enough for you to understand what's going on in the solution manual. But if you have questions, I'll be happy to try to answer them in the actual recitation session. Right. So again, let's go back to the questions. So this is the additional question I borrowed from Mazur. So we have white light that's between 400 and 700 nanometers that's incident on a diffraction grating that has 300 lines per millimeter. The interference pattern in this case is not simply alternating bright and dark fringes, but rather a sequence of red to violet rainbows located symmetrically to the left and right of the central fringe. What wavelength in either third rainbow, so either meaning either to the left or right of the central fringe, third order rainbow overlap the adjacent fourth order rainbow? Yeah. So before I actually start the calculations, which is actually just a couple of lines, I want to just allow you to visualize what's going on. So if you have just a diffraction grating with this, and if you have a single monochromatic light source, then the pattern you're going to get is going to look something like this. So you have your central fringe here, and to the right and to the left of this you have the first maxima, and to the right and left of that you have the second maxima, and so on and so forth. This is what you will get for a monochromatic light. Now if you increase the wavelength of this light, then these are going to move farther from the central fringe. If you decrease the wavelength of light or increase the frequency, then you're going to get closer to the central maximum. Right? So if you have light of wavelength higher and lower frequencies already in your source, then you're going to have all of that, and that's actually going to turn into the so-called rainbow. Right? So this pattern from this monochromatic light is going to actually expand into a rainbow like this, where I'm only showing the red and the violet part of the rainbow. So the red corresponds to a larger wavelength, violet corresponds to a shorter wavelength, higher frequency. And so this first order maximum for the monochromatic light is going to expand into this rainbow. The second order maximum for the monochromatic light is going to expand into another rainbow. Right? And these rainbows can potentially overlap. So there's a figure in the book where they're showing these rainbows where they don't overlap, but it's possible that by your choice of various parameters of your diffraction grating, that they would actually overlap. Right? And the story continues not just with the first and the second order rainbow, but the third and the fourth order. So they're going to look something like this. Okay? Now obviously this third order is actually going to overlap with the second order. The first and second are overlapping. The third and second should overlap, but for clarity, it's drawn separately here. So there's going to be some overlap between the third rainbow and the fourth rainbow. And so they're asking for, in the question, what wavelength range in either third or rainbow overlaps. So they're asking for the range of the wavelength that's in this region. Right? So this is going to start from some overlapping wavelength in the third rainbow to the longest wavelength in the third order rainbow. But that overlapping wavelength, the beginning of the overlap, happens to be the shortest wavelength of the fourth order rainbow. Right? So this corresponds to the wavelength, so this position corresponds to the wavelength of overlapping in the third order rainbow and the wavelength of the violet light in the fourth order rainbow. Right? So we can actually find this by using that relationship, that this actually corresponds to the same angular position for different wavelengths. Right? And then from that we can calculate this lambda 3 overlap, where the overlap starts in the third rainbow, and where the overlap ends is of course just the longest wavelength in the third order rainbow, which happens to be just 700 nanometers in this case. Okay? So I don't know if this was clear, but let me just go to the whiteboard and try to do this. Now, by the way, one of the reasons why I wanted to ask this question is to demonstrate how sometimes the parameters of a diffraction grating is given. So here they are giving you the number of lines per length, right? So from that you should be able to deduce capital D that we are using in diffraction grating, but sorry, small d in diffraction grating, but this is perhaps a discussion separate. But just try to go from this number, this 300 lines per millimeter to D, and see if you come up with a satisfactory answer. So this is the additional problem, and what I have is the third order rainbow overlapping with my fourth order rainbow. Right, so this is the third order rainbow. This is the fourth order rainbow. Right. So this is going to be the end. Is going to be what did I write with this? Let me see. I don't need to exactly copy what I've written there, but so long, and this is the theta that corresponds to theta 3. Right? So this is trivial. So the wavelength of this is just 700 nanometers. This one is this overlap starts here. It has 2, so it's either lambda short for theta 4 short, or this is lambda overlap for 3. And this is what we are looking for. Okay? So what wavelength of the third order rainbow will this correspond to? So I can write my basic formula over here. So E sine theta is equal to m lambda, and I can write for this position, I can write this twice. So one is going to be E sine theta is going to be 3 times lambda overlap, or the beginning of the overlap, you should read this that, or D sine theta is 4 times lambda short. Okay? And these two are equal to each other. So in this case, you don't actually need to interpret what this 300 lines per millimeter means. I should make this smallly, I think. I'm not really sure what we used in the actual book, but I think we were using smallly. Anyhow, but these two are equal to each other, so you don't need to turn that into what this corresponds to for t. I'm just going to write 3 times lambda overlap, or the beginning of the overlap is 4 times lambda short, so lambda overlap is 4/3 of lambda short, and that comes to 4 times, the limit is what? 400 nanometers divided by 3, it comes to what? 5? Is that right? Yeah. So 578 nanometers. So the overlap is going to take place from 578 or 533. I wrote in my notes 533, so I believe my notes more than I believe my calculation on my feet. So from 533 nanometers to 700 nanometers. Okay. What the important thing here is really not the calculation, but the conceptual understanding. Right? So as you see, it's just one line. It's just a simple division, which I might have done wrong, but that's not the important thing. The important thing is conceptually understanding what this looks like. As I said, this could also be an opportunity to actually turn some information that's given in one form to another form, but that's going to be for another day. Okay. Thank you.